graphs of logarithmic functions. So today I'm going to talk about what the graphs of simple logarithmic functions look like. So what I mean by simple logarithmic function is the function in the form y equals the logarithm in base a of x. Now this is actually a family of functions because the number a, the base, can take on many different values, and therefore we need to distinguish some typical cases. And this is exactly what this table here is for, because there are two major situations we should talk about. In the first situation, a, the base, is greater than 1. For example, a would be 2, like the base 2. And in the remaining, or the second case, the base is between 0 and 1. You already know that for the base to be valid, it has to be positive and different from 1. And hence, there are only two possibilities for it to be in regard to 1. It's either greater than 1 or less than 1. Of course, in both cases it has to be greater than 0 as well. Okay, so let us look at these situations here. Let us start with the first one, when the base is positive and greater than 1, as you see here. So you already know that the logarithm in base a of x, this function, is the inverse of the original function y equals a to the power of x. So these functions, these two functions, are inverse of each other. So this one is the inverse of that one, and that one is the inverse of this one. The fact that they are inverse is depicted in the picture, because you can see that the logarithmic function, which is here in logarithm in base a of x, is the image of the exponential function reflected in this line. So you see that you can imagine this original function y equals a to the power of x to be reflected about the diagonal of the first and third quadrant, and what you get is the graph of the logarithmic function. So if you remember the properties of exponential function, you should be able to recall that the exponential function graph, the graph of the function a to the power of x, passes through the point with coordinates 0 and 1, because a to the power of 0, so if you substitute 0 for x, a to the power of 0 is 1, and also it passes through the point with coordinates 1 and a, because a to the power of 1 is just a. So the original function has to pass through these 2 points. Also, you may remember that if you reflect the function about this axis, then the coordinates of each of its points are interchanged. So, for example, the original function passes through this point, and the reflected function should pass through the point with coordinates 1 and 0. So we interchange these two numbers and get 1 and 0. Also here, these numbers here the coordinates here were 1 and a, and here I have a and 1. So you see how it works. Now, we should be able to describe the properties of the logarithmic functions if we remember some properties of the original exponential one. So, for example, let us look at this picture. The domain of this function, so this red function is the function f. This is what I mean by f. So this is the function, and its domain is represented by only positive numbers x. You cannot calculate logarithms from negative numbers or from 0. And the reason for this being true is the fact that the domain of the logarithm has to be equivalent to the range of the exponential. So the range of the exponential function was only positive numbers. So therefore you have positive numbers here. As for the range of the function f, of the logarithmic function, the range consists of all real numbers, and the reason for that, you can see it either from the graph that it can have any value y as its function value, but it is also the consequence of the fact that the domain of the original function a to the power of x was the set of all real numbers, and since domain and range get interchanged when we create the inverse function from the original one, this then has to be true. Now, if you look at this function, logarithm in base a of x, you see that it's increasing, it's strictly increasing. It is not bounded from below, and at the same time it's not bounded from above, so there is no bound, no lower bound nor the upper bound there. It is 1-to-1, and the reason for that is that the original function was 1-to-1, so also the inverse has to be 1-to-1. F has not got any strict maximum point, and it has not got any strict minimum point. And now the interesting part, the asymptotic behavior. So look, as x approaches infinity, y approaches infinity. So it is strictly increasing, so it will increase without limits. Now also, as x approaches, now we cannot approach negative infinity here because we have the restricted domain, but we can approach this left boundary of the domain, and it's 0, so we can approach 0 from positive values. So if x approaches 0 from above or from the right, let's say, then y approaches negative infinity, as you can see here. As for the second situation, now let us concentrate on the situation in which the base is between 0 and 1. In that case, for example, a might be 1/2. In that case, you may remember that the exponential function had this graph. This graph also passed through points with coordinates 0 and 1 and 1 and a, but since a was less than 1, it was in this shape. It took on this shape like this. It was decreasing and so on. Now, if you reflect this function on this diagonal, so if you create the image, the reflection of it on this diagonal, you get what is the logarithm in base a of x. And you see that the logarithm is also strictly decreasing as it's represented by the picture, and you see that it approaches the vertical axis without any limit and so on. So let me go through the properties of this logarithmic function. So first, notice it passes through the point with coordinates 1 and 0 and through the point with coordinates a and 1. So these are two important points on the curve. And now let's talk about the domain of this function. So this function is the function f. So the domain of this function consists of all positive numbers. Its range is represented by all real numbers. It is strictly decreasing. It's not bounded from below nor bounded from above. It's 1-to-1 because also its original was 1-to-1. It has not got any strict maximum point nor any strict minimum point. And as for the asymptotic behavior, as x approaches 0 from the right, like this, when we approach 0, y approaches infinity. And as x approaches infinity, y approaches negative infinity. So these are the basic properties of simple logarithmic functions. Now let us talk a bit about the asymptotes. So the original exponential function a to the power of x had the asymptote, which was the horizontal asymptote, and it was the axis x. It was the x-axis. It was its asymptote, so it meant that the graph got closer and closer to this asymptote but never crossed it. Now, if you reflect this function on this diagonal, also the asymptote gets reflected, and this means that the logarithmic function will have also an asymptote, but this time not the horizontal asymptote, but a vertical asymptote. You can see that this line is reflected as this one. So the y-axis is going to be the vertical asymptote of the logarithmic function. Since there was no vertical asymptote in case of exponential function, then it means that there is not going to be any horizontal asymptote for logarithmic function. So the logarithmic function has only the vertical asymptote. And this is also true here in this situation, because also here the exponential function had the x-axis as its horizontal asymptote, and therefore its inverse must have the y-axis as its vertical asymptote. So the simple logarithmic function has only the vertical asymptote, and it's the line with the equation x equals to 0. So this is the vertical line passing through the origin of the coordinate system. Now, the final question about these functions is the following: when is the logarithm defined? Okay, so in general, when you have y equal to logarithm in base a of a different function g of x, this logarithm is defined only when g of x is positive. Since you can calculate logarithm only from positive numbers, then you have to require that g of x be positive in this equation here. Now, let me generalize a little bit. So these functions here were the simple logarithmic functions. This is the name that we assigned to them. But of course, you may imagine that we can tweak them a little bit and we can think of more general situations. So here we have the functions related to simple logarithmic functions. Some people call them logarithmic functions, these functions which are more general. I will use the name functions related to simple logarithmic functions. So there are two families of these curves or these functions. The first one is the family of functions of the form y equals k times logarithm in base a of x. So the only difference is if you compare this with the simple logarithmic function, which was y equals logarithm in base a of x, this function is k times the original one. So let me denote the original function f sub 0. So f sub 0 is this original function. And now you create a new function by multiplying it by a factor of k. Now k has to be different from 0. And the question here is, what is the impact of the change in the value of k on the graph of the function? So what impact does it have? So we can research this by looking at the model in GeoGebra, which I have prepared in advance. And what I have here is the graph of the logarithmic function, logarithm in base 2 of x. You can see it here, this red curve. It passes through the points 1 and 0 and through the point a and 1. A is the base, it's 2 and 1 then. And it's strictly increasing and so on and so on. Now, here I have the slider k, which has currently it has the value of 1. So this function is identical to simple logarithmic function. Now, look what happens if I increase the value of k. So if I increase k, the graph is scaled vertically away from the horizontal x-axis. So everything becomes stretched out in the vertical direction. The graph is stretched away from the horizontal axis. This means that the original position of this point, for example, was here, so it got twice as far from the horizontal axis as was its original position. This is also true for points below the x-axis. They also get away from it when k is positive and greater than 1. Now let me decrease k back to 1 and see what happens if k is less than 1 but still positive. If k is less than 1 but still positive, let us imagine, for example, k equal to 1/2, you see that the graph is also scaled vertically, but this time it's shrunk in the vertical direction, and it's shrunk towards the horizontal x-axis. So if k is 1/2, it means that every point of the original graph got closer to the x-axis, and it got to the distance which is exactly 1/2 of its original distance. Now what happens if I decrease k further? So I get to this forbidden value soon. K cannot be equal to 1 because then it stops being interesting, but now I can get to negative values. So if k is negative, you see that the graph gets reflected on the x-axis. So what I get is the reflection of this graph and a corresponding stretch or shrinking in the vertical direction. So for example, when k is only -1, the relationship of this graph to the original logarithm in base 2 of x is that it's just reflected about this horizontal x-axis. Nothing changed, just it's flipped like that. But if I take k equal to -2, you see you get a stretch. So it's the reflection and the stretch combined. And if k is -0.5, for example, it's the reflection and the shrinkage in the vertical direction. So this is the impact of k. Now we can come back to this presentation here and ask another or look at some other family of functions. So this was the family of functions in the form y equals k times logarithm in base a of x. Now let us consider another more general family of functions. This time the functions in the form y equals k times logarithm in base a of x minus m in brackets plus n. You may remember this game with m and n. It had to do with shifting or translating in the horizontal and vertical direction, and this is exactly what's going to happen here. So this time we have to compare this function f to the original function f sub 0, which is going to be the function k times logarithm in base a of x. So the function mentioned a minute ago in this first part. Okay, so imagine you have this function f sub 0 and you have this one which is called f. The only difference is that there is m and n there. If m and n equals to 0, then you get this function becomes identical to f sub 0, but in general case m and n are different from zeros, so therefore you may have some these values may have some effect on the graph, and we are going to explore that. So we are going to answer the questions: what is the impact of the change in the value of m on the graph of the function here, and what is the impact of the change in value of n on the graph of the function. So let me go back to the model. Here I have the logarithm in base 2 of x, which is multiplied just by 1, so let me leave it at this value. So I will leave k being equal to 1, and what I can do now is I can shift m or change m. So if I increase m, you see that the graph gets translated to the right. So for example, when m is 2, the graph got translated to the right by 2 units. It got translated through 2 units to the right. So for example, this point here had its original position here. So the original position was 1 and 0, and it got translated 2 units to the right. The same goes for this point. So you see that together with the function, also its vertical asymptote, which in its original form was this x equals 0 line, also this vertical asymptotes gets translated. So if I translate the function, also the asymptotes is translated by the same number of units. So for example, when m equals 5, the vertical asymptote is x equals 5. This point has the x-coordinate of 6 and this one of 7, because these are increased values of the original coordinates of these points, which were 1 and 0 and 2 and 1. Okay, so this is the effect of m. If I decrease m below 0, then I get translation to the left. Okay, so for example, if m is -3, the whole thing is translated by 3 units to the left. Okay, so this was the effect of m. Now, what is the effect of the change in the parameter n? Since n is added to the value of the function, then one can expect that it's going to increase or decrease the value. So if I increase n, all the values of the function increase. So for example, when n is 1, all the values of the function increased by 1. So all the points of the graph of the function got translated through 1 unit upwards. So if n is 2, then I get the translation of 2 units upwards, or through 2 units upwards. Okay, so n changes the vertical position of the graph. Okay, so this dashed line here, this horizontal dashed line here, is the line which originally corresponded to the horizontal axis, and it's written, or it's there just for our convenience, so that we can imagine the original graph which is placed in these dashed axes, which I would say. Okay, so imagine now the general case. Imagine that m is 2, for example, and n is, say, 1. Then you see that the graph of the function is translated by 2 units to the right and through 1 unit upwards, and together with this graph also the original axes are translated. The vertical axis, the original vertical axis being the asymptote, and there is no meaning to the original horizontal axis. It's there just for our convenience, like that. Now, if I change k, you see the most general case now. If you change the value of k, you then translate not the logarithm of x in base 2, but you translate the function 2 times logarithm in base 2 of x. So this function is translated by m and n in the horizontal and vertical direction. So you may imagine that we start with this function. This is the function 2 times logarithm in base 2 of x, and we translate it by 2 units to the right, like this, and through 1 unit upwards, like that. Okay, so you see what the effect of these parameters is on the function, and now you will be able to sketch the graphs of these functions by yourself and do it very easily.